Hello, AP Calculus students. We are going to take a look at an definite integration problem in this example, where we actually find ourselves integrating across a discontinuity, as you can probably tell by the title of the problem. So let's just jump right into it, shall we? So the first thing that you're going to want to do with this, since it does ask that we sketch and shade this region, that's going to be our first priority, because I think that's going to give us a great deal of insight into how we will find this particular area. So the piecewise function can be sketched pretty easily by looking first of all at the top piece. Negative 2x plus 7 is equivalent to our function. We recognize that as being just a straight line where we have a y-intercept of positive 7 and a slope of negative 2. So we find that 1, 2, 3, 4, 5, 6, 7 is located up here, and a slope of negative 2 would take this thing down 2 blocks and over a block, down 2 blocks, over a block, down 2 blocks, over a block. And what I'm going to do is I'm going to stop there, because I see that the domain restriction for x is x less than or equal to 3, and that's exactly where I have arrived. So basically what I've got going on here is this straight line that looks something like that. And yes, it would continue off in the positive y direction, negative x direction, but we may not be dealing with that particular part of the graph when we find the area. We'll see that in just a moment. Now, as far as the other sketch, I'll use red to sketch the f of x equivalent to 4. Y is equal to 4, which is just a horizontal line. And I'm going to be very careful to only graph that for x values that are strictly greater than 3. So here is my x value of 3. If I count up to 4, I know that I would put an open circle there, because I'm not allowed to use the x value of 3, nor do I want to have a situation where I no longer have a function. That would be bad. So we're going to go ahead and sketch that. And let's see if we can kind of make that, hug that line a little bit better. There we go. And that would continue off forever. But now we start to pay more attention to what our definite integral is wanting us to do. We are only going to find the area underneath the curve between 0 and 5. So obviously we see our 0 right here for our x value, and our 5 is right here. So if we use vertical lines to kind of depict our leftmost and rightmost boundary, and we throw in the added fact that the x-axis is always going to serve as a boundary in this situation, we have kind of an interesting situation here. You know, normally we have a region that is completely enclosed and thus would, say, serve as a fenced-in pasture. I think I made this joke with one of my classes, where let's say we have this cow roaming around our pasture. Well, in this particular field, the cow could find its way out, and that's not a good thing ever, right? But really what's happening is something completely different here. We don't really need to say that this is entirely enclosed, because that's really not what this area is about. What this area is more about is what will we have, what kind of space, how much space do we have underneath each of these curves and above that x-axis. So we're essentially just going to find the area of this particular shape here, which, as you can see, that shape is really going to be a trapezoid when we kind of think about this vertical partition. And then our other shape, which I'll just go ahead and continue to highlight in the same color underneath the red line, is going to be a rectangle. We still definitely have regions below these curves, in other words. And of course, we could think about there being this partition right here. So now the problem really reduces itself to a very simple geometry situation. So as I said before, the integration of the f of x from the lower boundary 0 to 5 can be found by taking first of all, the area of what I'll call region 1 here, the trapezoid. The formula for the area of a trapezoid is 1/2 times the sum of the bases. Well, the bases would basically take on the values of 7 and 1. This is sort of one of those trapezoids that's sitting on its height. So 7 plus 1. And then the height, as I said, is going to be the bottom, which is 3 in this case. Because all of this trapezoid here lies above the x-axis, we can construe this area as being positive. Likewise, the other shape, number 2, the rectangle, is all above the x-axis, so we have another positive area. And you can probably see that this is a 2 by 4 rectangle. And when we just do our simplification here, 7 plus 1 is 8, divided by 2 is 4, times 3 is 12, and then 2 times 4 is 8. So we end up getting an answer of 20. Now, if you're watching this video, say outside of Avon High School, you might wonder, well, is there an approach to find this integral by actually performing some antiderivatives? And the answer is yes. You could still perform the antiderivatives of both the function negative 2x plus 7 and 4 and run in the appropriate boundaries and come up with the answer of 20. Doing the problem this way does require a bit of a sketch in order to see it, but the purpose of this particular video for my class is just reinforcing the fact that the definite integral is indeed the area of under a curve. And in the last point that I wanted to make here is that we can indeed integrate functions across discontinuities. That's kind of a strange idea. That's something that we would never think about doing with derivatives. Hey, how would you find the derivative of this particular graph at x equal 3? That might be kind of tough. It might be tough to draw the tangent line at this point because we don't really have a continuous function flowing to the right side from that point. But taking an integral across a discontinuity, a completely different idea, and it's an idea that you'll actually expand upon in a Calc 2 or say a Calc BC class. So anyway, I hope this helped, and I will see you at the next video.